So, and this is the technique that we could have used on that problem that we just had. This one up here, the purple one. All right, we could have used on that. Solving an exponential equation or equations. All right. So if we have a say a variable in the exponent, such as this one, all right, you can use a definition of a logarithm on that and get the answer, and there's nothing wrong with using that strategy. But another strategy is to just take the log of both sides. That's what it's kind of called. So if you take the log of both sides, you're going to get the log of this equals the log of 130. And then what happens is that when you apply that one law of logarithm, that one property, logarithms, what happens to this x? Where's it going to go? In the front, right? So it's just another way of solving. We could have used this same idea on that one problem where we had that negative k, and we just Chrissy wrote it as a natural log, and we could have just taken the log of both sides, and we could have got the same answer. It doesn't make any difference. It's just a different way. So now we have this, which is pretty simple. We just got to divide by the log of 3, okay? And this is all, they're just numbers, so it's okay to do that. I think I'm just going to quickly pull, oh, I can't. I keep forgetting that. I'll pull up a calculator here. So let's see how I can get this to work. 130 log divided by 3 log equals 4.4. So it's just another way of solving that type of exponential equation, is just to take the log of both sides. And it really doesn't matter what's in the exponent. We just take the log of it, both sides. So even if we had something like, here, let's do this. All right, so we have something like that. All right. We're just going to take the log of both sides. And then this is just going to jump out in front. So maybe it's easier. I don't know if it's any really easier. It's just another way. Just make sure that when you divide by the log of 2, that you don't divide these two things, all right, and make it the log of whatever that would be, 270. All right, we don't want to do that. We got to treat them separately. So you got to treat it as the log of 540 divided by the log of 2. Okay, that's equal to negative 2x plus 1. So I'll do this. 540 log divided by 2 log equals 9.08, I think it rounded to. And then I would just go ahead and solve it out, you know, like you would normally, that whole thing. Okay, so that stuff's in there, solving just exponential equations using that particular method. Any questions on what we just done that part? It's pretty. And again, you can use the definition. You don't have to even use this method if you don't want to. It's completely up to you. Yeah.
Well, really. Yeah, but I can see it being a little bit easier when you have all those extra things.
I would agree. Then they have these log equations they want you to solve. So they kind of look like this. So log base 4 of x plus 2 equals log base 4 of 8. All right? So, so I was looking at some of these and I was thinking, well, they're both, so, I mean, this is the same thing, right? It's both base 4. So really, the only problem here is figuring out that, right? Because they're the same base. So there's nothing there that is really difficult about that. You're just figuring out, well, shoot, x is 6. Because the bases are the same, okay? So they have some couple like that. And I looked through in almost every one of them, the bases are the same. All they're doing is just changing what's on the inside of the of the log there. So, I mean, there's a couple of them that like here, I have one like this. So this one here is a little bit, because I have that 1 there and it's kind of messing me up and I can't do much with that. But let's think about it for a second. So if we could somehow replace this 1 here with something that looks like a log base 4, then we can do this problem, because this would be a log base 4, this would be a log base 4, and this would be a log base 4. Right? So if we could just figure out, well, how could I get the log base 4 of something equal to 1? Right? Does that make sense? What we're doing there? So we're going to take this number here and replace it with a log that's base 4. I just got to figure out, well, what would that look like? Does anybody have any idea what would be in there that would make it work? What? 0, maybe. Okay. Michael says 4. All right. Let's check it out. So let's say we put an x there. And let's use that definition of a logarithm. So we're going to take, here's my base, to this power is equal to this number.
Log of 4, right?
So it's just going to be 4, right? Yeah. Okay. Well, now that I know that, I can use that every single time I have something like this. So I'm going to have the log of x plus 6 base 4 equal the log of 4 base 4 minus the log of x plus 4 base 4. Now, everything is in the right. Base 4, base 4, base 4. Yeah, it's not quite that way, but watch what happens here. So we got this, right? Now, when we have log base 4 here, and we're minusing, I can write that as a single log. And what would it be? What would I be writing that inside here? What would go inside there? Right, because it's a minus, right? Okay, so see, this is a minus. So we know that's got to be division. So we're going to take this and divide it by whatever's in here. Now we can get rid of the log base 4s. And we have this really nasty equation. Well, let's go ahead and cross multiply on it. So I'm going to FOIL those two. Set it equal to 0. And then I just got to solve that. Hope it has an answer. I don't think it's going to, though. No, yeah, it will. Okay, we can't factor it because it's not going to factor, but you can use the quadratic formula on it. You probably remember that. Maybe. Look familiar? Negative b plus or minus the square root of b squared minus 4ac all over 2a. Yeah, I got a couple bobs. Yeah. No stupid questions.
What gives you at that point when it's like x squared plus 10x plus 1 equals 0? Why can't you just be like minus 20 and then minus 20 and be x squared plus 10x equals negative 20? Could you not do it that way? Like just solve it with that itself?
So here's this. Like this, right? And then what are you suggesting?
Just do it like minus 20 from each side.
Okay.
And then I guess it's more complicated.
Were you thinking you could square root?
Yeah, but then.
The problem is this,
Yeah.
right?
Yeah.
Yeah. Yeah. Whenever you have a quadratic, I mean, I shouldn't say that. I would say that almost every time you have a quadratic, you always set it equal to 0. And then the quadratic formula works every single time. So you can use that. Factoring will work sometimes, but we can't factor this because it doesn't factor. And we could graph it and we could get some answers, but anyhow. Okay. The one that I made this one up kind of, but the ones that you'll get will most likely work out because they have people that make sure they work out. All right. But the idea is the same. That what you have is you want to make sure that you're replacing this by something with log base 4 or whatever base you're using so that it works out. Okay. I just really don't see much in there that's much different than what we're doing here. They have a couple natural logs, but same idea. So basically, we're talking about, solving these exponential type equations like we did on that one, okay, or these log equations that are kind of like this, right? So I can do another one of those log ones if you want. I mean, if you want, we can look on 337 and see if there's one there that you're looking at and saying, there's no way I can do that. That's where they are. Do you want me to do another one of those? What would you guys like? Yeah? Is there one on 337? Do you see one on 337 that you would like to, we could not want to do? 39?
59.
59?
We leave it after 4. Yep.
Is 59 one of our problems?
Yeah.
Okay.
Yeah, it's not that one.
So yes, do it, or no, don't do it. Is it one of them? Let's see.
Do it.
337. So 59 is not one we're doing though.
Yes, it is.
It is?
It's one of
Or
the
am I looking at the wrong one? Wrong stuff? Is it? It's 337, right? I have 5 through 31 and 4 through 57.
Yeah. Yeah, 59 is not one of them.
Mm-mm.
Oh, you can still do it, right?
I'm looking at it. If we take the log of both sides, that's not going to work because you can't distribute the log. You'd almost have to graph that one to get it. Well, okay, I see kind of what they do here. We could do one like, do you want to do it? Which one do you want to do, 59 or 57? I see how they do it now, but.
Yeah, it seems a little bit more complicated. Will a problem like that be in the test?
Nope.
Oh.
So, here's what they're saying, is that this is a form of a they're saying that you should be able to take this thing and factor it. So in other words, you should have a 3 and a 3, or a 1 and a 3. And this would have to be like an x, and this would have to be an x, because when you multiply that, you get 2x, right? And then we need to get a x plus 1 here somehow. So let's see. I'm looking to see 4. We can either go 2 and 2 and 2 is going to be, will that work? Yes. Would I have to do 1 and 4? So that's going to be 6. Yeah. Yeah, so we got to do 1 and 4, huh? So the 4 is going to go here, right? And 1 has got to go there. And 1's got to be a minus, 1's got to be a plus. So that's 3, the x. And this is 4. I think this has got to be positive, and this has got to be negative, I believe. So let's see if that works. So that's going to give us 3x, 2x. And then 1x plus 4 times 4 minus 1 times 3 minus 4. This is just going to be 3 to the x, because 1 times that. I think that follows up, factors out, right? So then, this is set equal to 0. So then we would have 1 to the x minus 1 equal to 0, and 3 to the x plus 4 equal to 0. This is how they do it in the book. So this is x is going to have to be 1 here. That's the only way that's going to work. And 3 to the x equals negative 4. And then if we logged it, problem is you can't take the log of a negative, so you'd have to pitch that solution all together. But we wouldn't have that on a test. And you know, I think, yeah, that's how they want you to do it. But I wouldn't put anything like that. That's kind of a, like I said, it's kind of a, I don't know about that one. But getting back to, did you find one on, another one like that one on 337?
No, just anyone.
Just anyone?
Yeah.
Okay. So 5 through 31 odd. All right. Here we look at one like this, 27 log base 3 of x plus 1 plus log base 3 of x plus 4 equals 2. So here's 27. Okay, it looks like this, right? So here we have a plus with two same base logs, a plus. So what is that? How can we rewrite that as a single log? What's that going to look like? Multiply. So it's going to be log base 3 of what? Yeah. And that's going to be equal to 2. Okay, so then we just do this. And here I would just apply the definition. Okay, so we're going to take the base 3 to that power is equal to this. Since it's a quadratic, got to set it equal to 0. So we'll slide that over. So it looks like that. Did we do that right? Did I write it down right? X plus 1 plus 4 times equals 2. 5x plus, yeah. And you got to use the definition on it. And it's log 3. That's a 9. It just doesn't turn out. You just have to use quadratic formula again. You can't factor it. Because this is a 9, right? So, well, I mean, this is not a 9, but this was a 9. Here, I'll do it. So it's 9 equals x squared plus 5x plus 4. And if you subtract that 9 over, yeah, you got it, because it doesn't factor. I'm surprised that they didn't have a factor. Maybe that's why there's an asterisk in front of it. So we can do the quadratic formula. So -5 plus or minus square root 25 minus 4 times 5 times 1 all over 2. -5 plus or minus the square root of 5, because that's just 20, all over 2. Now, but the negative answer won't work. Most likely. Yeah, because you can't take the log of a, so there's only a certain number that's going to work here. -5 minus the square root of 5 is going to be too big. Negatively, it's not going to work. But -5 plus the square root of 5, that might work out okay. Divided by 2. Okay, so my bet is that, see this one, this here, maybe it'd be all right. So -5 minus the square root of 5, which is a little over 2, that'd be a 7, that'd be 3.5 negative. But that won't work. Whenever you have a situation where you're squaring like this and you're solving the quadratic formula, there's always a chance that one of them isn't going to work. Right? So you can't take the log of a negative number, right? So it's got to be, the only one that's going to work here is the -5 plus the square root of 5. That way, you'll get at least get a positive number when you put it in for x. You're just getting a solution that isn't going to work.
But then we get rid of the log when we get the.
Yeah, but the original problem was a log.
Oh, okay. So when we plug it back in.
Right. Right. And you could actually kind of beaten this up a little bit, but so this is the log of x plus 1, 3. So I'll put a 3 here, parentheses, x plus 1. Get rid of this parenthesis, I don't want that in there. Plus this 3. And this one is x plus 4. There's that. And then if we put in y equals 2 on the bottom here, there's your answer. See where they cross? That's why there's only one answer to this instead of 2. So if I went like this, let's see what happens. If we go parentheses -5 plus square root of 5 divided by 2. So it's 1.38 negative. Oh, I see what the problem is. This is a -5. So that makes that a negative, which makes this a 25. Got it. Right. Or 45, sorry. It makes it a 45. That makes a difference. I really butchered this. See, that's the same answer. There and there. I just didn't put that negative in there, so that's how I got screwed up. Okay. But there's only going to be one answer. So you really have, you just kind of, the negative is probably not going to be an answer here because it's just not going to, you can't take the log of a negative number. So you kind of have to watch it when you're doing those that you don't. Normally it's to be a plus or minus, but the minus gives us a negative, so we can't have a negative in here. Even though you're adding 1 and 4, it's just too much. But you can check them out by graphing, which is kind of slick, to make sure that you're doing it correctly. I don't know if it really helped very much, but I gave you another example. Okay. Sweet. Anything else on that particular section? Okay. So let's do this. Let's go take our normal. We're about to our normal break time anyway, and we'll come back and do 4-7, which really won't take very long. I'll give you some problems to work on, and then we'll kind of go from there, I guess. Oops. So I'll just repost it.
Okay. And then for the quiz today, so for the quiz on Monday, I wasn't here. Do you want me to take that today, or is it like past the time I can take it?
Oh, heck no, yeah, actually until March. I can't even remember the exact date, but it's on the syllabus what day I have to make up all those quizzes and stuff.
Okay. And then for today, do you want me to do the quiz? Because I didn't do 4.5. I could just try it and then see if I can do it.
Just try it.
Okay, I gotcha.
Yeah, it's relatively short.
I gotcha.
Okay. Hi.
So, I don't know if I missed something when I missed last week. For this first question here, when you, so I went through and did, but it's not the
Yep.
same rate,
Yep.
so now I'm kind of lost.
So you just need to find okay, so one thing that I know it's not the same. Okay, let me see what you're doing here. Okay, so you're finding the rate. You are correct. Okay, so you're correct. It's not the same rate. Okay, it's still growing. So what you want to do is find a number that best represents all these. So how would we find it?
Average.
Yep, an average. Yeah, and it's not, again, when you're dealing with real stuff, it's never really pretty, but
Right.
that's
Okay,
okay.
so find an average.
That's okay. Find an average. Hey, I knew that. I saw that you didn't, and I thought, well, she always turns her stuff in. And you emailed it?
Yeah.
Oh, I don't care. Sure, this would probably be good. Well, thank you. Was it yesterday or when did you do that?
Monday.
Monday? And I just missed it, huh? Okay. Sweet, thanks.
I only 4.34, but I wasn't here last class because I got snowed in Washington. And I was just wondering if I'd be able to.
You were what?
I got snowed in Washington.
Seattle?
It was southern of Tri-Cities.
Oh, yeah.
They got 20 inches of snow.
Oh, man, it's crazy.
It was.
Did you have to go through the gorge to get back?
Yeah.
Oh, my
Yeah.
God. They were just talking about.
The river is crazy too.
Oh, yeah, they were just saying how some people
Oh,
were
yeah.
18 hours they were stuck.
18, yeah, I know, and that was the highway I had to come down, and because they got stuck, they closed it, and I was like,
Poor you.
anyways, I was wondering if I could take that test last class, or if I don't take it, if it's gonna have like a big effect.
We have until whatever March date, whatever I think it is at the 8th. That's probably like the 11th or the 13th, I think I said is those days to get the quiz done. So you have till then to do it.
Okay, when can I take it? Like, when is a good time? During class?
You could do it.
Can
Well,
I go to the testing center?
I mean, you could, right? You could go to the testing center. I mean, you know how the length of the quiz is. You know, they're not super
Yeah,
long.
yeah, yeah.
So you could either do it. You could you could do it after class. You could do it. You could maybe do it next Wednesday if you want to really punish yourself and take the test and the quiz at the same time. But that's a possibility.
Too
Then.
bad.
Yeah.
That sounds like a good plan.
So that might be a good time to do it.
All right, thank
Okay.
you.
Oh, you're welcome. Hey.
I wasn't here on Monday, so I missed the quiz on Monday.
Yeah.
Can I make up that?
Yeah. You have until I think March 11th, whatever the day in the syllabus is, to make up all those
Oh,
quizzes technically. So I know she just said something about maybe doing it next Wednesday after the test. So you can do it if you want to.
okay.
Or you can, I mean, you can set up a testing center thing, or you can do it you know, after class, whatever you feel like you want to do. Just let me know. Okay? Yeah. Page 279, is that about right? Yeah, 279.
Hey, I was wondering if you have any quizzes to pass back to me, because I was gone, I think, in the class, so we can pass back to you.
I probably do, but I'll go get them, so we can do it today. I'll find some time for it, sure. Page 279. What the heck is this thing? Page 279, enter. 5 and page.
Do we have a quiz today?
Yeah. It'd be on whatever we did Monday, so that would have been 4, 4, and 4, 5. It's pretty short though. I'll try and make those ones pretty short. We'll do a couple more here now. Okay. All right, so 4.7 basically just talks about, they call it financial models, so it's basically talking about loans. Okay, but to be honest with you, okay, the really loans that we have anything to do with are car loans and housing loans, which are not in this at all because they're figured in a different way. So most of you, I mean, I'm probably telling you something you already know. Housing loans, of course, are amortization loans, which is a whole different ballgame. I mean, it's really hard to come up with how those things are really figured out. Okay, but the main thing is what they pay off your interest and then pay off your principal, and then the remaining amount of your loan is being applied to an interest rate, and it's pretty complicated how an amortization loan is actually figured out. Most of the time, if you really get into it, you have to use like an Excel spreadsheet to really see what's going on. Okay, so there's not just a equation or formula that's going to figure that out for you. All right. Car loans also are somewhat I was reading some stuff on it today. They also use an amortization value, which I knew they did. So it's not a real straightforward as far as how to figure it out, but this would give you an idea of kind of how they're done, and I can share with you a formula, as I looked it up today, on what they kind of do. At least I thought I put it in here somewhere. But anyway, so we'll take a look at a couple of loan formulas that are in here, and then we can go from there. So the first one they talk about here is just a simple interest loan, right, that you were exposed to years and years ago. Well, not years for you guys, years and years ago for me. All right, simple interest looks like this. Okay, where you're given a principal, and you're given a rate, and you're given a time, and you just want to basically, so if you loan somebody some money and you want to know, apply an interest rate, okay, so if we had $500 at a rate of 5%, over 2 years, okay, this would be your principal, this would be the rate, this would be the time. So the amount of interest that would be paid would simply be 500 times 0.05, because you got to change that to a decimal, times 2. And that's just simple. That's just a real simple interest formula. Okay. Now that's the interest. Okay, so that's how much interest that person would be paying. All right. But again, that's just really simple interest. Okay. That's how that. So when you see simple interest, that's what you're going to use. Okay. But most loans and credit card balances, stuff like that, are compounded. And even like a credit card thing, they got in trouble years and years ago because they were reporting the wrong interest rate. And there's a difference between an annual interest rate, APR, which you guys hear about, and just an interest rate. And they were doing an interest rate, and they weren't telling people what the APR was, when the APR was actually higher. So they had to start reporting APR. Okay, so the formula for this looks like this. Okay. And in this case, P is your principal. R is the rate. N is the number of times it's compounded. So that's when the rate is applied. And T is the time, of course. All right. So this one's a pretty common, mathematically it's a pretty common interest formula because it's a little bit more applicable to what a loan really is, better than simple interest. Okay. So let's play around with this a little bit. So we'll take $1,000. 4%. We'll go once a year. We'll just do 1 year. All right. So we're going to go 1,000. That's my principal. 1 plus. Change that rate to 0.04. Put a 1 in here. Okay, because it's compounded yearly. This would be annual. Once a year. When you see the word annual, that's once a year. And it's just going to be 1 times 1, which is 1. All right, so if I type that in, and actually you're better off typing it in decimals, but I'm going to try putting this little calculator here, which isn't great. So I'm going to go parentheses 1 plus 0.04 divided by 1. I'm just typing the whole darn thing in. Parentheses to the 1 equals 1.04. Now I'm going to times that by 1,000. and that would be 1,040. Okay, so that's probably what you got. So if you type this straight up in the decimals, you should get 1,040. Okay? So the idea is, what would happen if we change this, keep the rate the same, but we change the number of times it's being compounded to a different value. So another one would be semi-annually, which would be twice a year. So we put that there, and then 2 times 1. All right, so we would do that. So I'm going to clear that out. So now you should get 1,040.4. Is that correct? All right. Okay. So it's a little more, but you would expect that because you're compounding that interest rate twice. All right. So let's jump ahead a little bit here and let's do it monthly. All right. So we're going to take 1,001 plus 0.04. We're compounding it monthly, which is what most loans do. Okay, so put that in and see what you get. Tell me when you get something, just shout it out at me here.
1040.74.
1040.
74.
Okay. So if we take, so here's my interest. So this is the interest that I'm paying. Everybody agrees with that part, right? Okay. So here's what I was telling you about. So if you take 40.74 and you divide that by 1,000, this is how much, this has been your interest rate. Okay, so you can see, so what is that if we divide that by 1,000, what do we get? 0.04074. So see, that's an APR. Okay, which is higher than, not much higher, but it is higher than that 4. So if you did it with a big lot of money, it would make a difference. All right. So what was happening is that credit card companies were just reporting this rate rather than this one, but now they have to do the APR. So it's a different situation. All right. Okay. Anyhow, so here's that one. So let's do this one now. So let's go daily. So that's going to be 365 times to the 365 times 1 up here, which is 365. Okay, tell me what you get for that. So this would be compounding daily.
1040.8.
Now, sometimes it's a little unsettling because you would think that you're compounding something daily at interest, and you should have a lot more money here than what you really do, right? So then what I usually do after that is say, well, okay, try this out. So we're going to go 365 times 24 times 60, which is daily times hours times minutes. So that means it's being compounded by the minute. And Desmos will be able to handle that. Did you get it? It didn't? It should. I've done it before. 1040.81. Okay. So, see, it's only like a penny more. So you would think again that, man, how can that be? Well, what's happening to this 0.04 number? It's getting really small, huh? Okay. It's getting very, very small. So that's why you're not getting anything out of that. You would think it would go better to do it. So this could actually, you could do it, and it would be something that was called continuously. So that means that it's going while we're talking. It just keeps going and going and going and going. And when you have something like that, it starts to look like this. Bless you. All right. Which becomes our thing for E. So this just becomes E to the N. Okay? So when you have a loan that's continuous, then you're just going to use what we used to call PERT. So the principal times E to the RT. All right? So if you wanted to find something that was continuous, then you would just take 1,000 times E to the 0.04 times however many years you want to do it, which we just said 1. And that should be pretty dang close to what we got for a minute. Try it out and see. What did we get? Almost exactly. What is it? 1040.81? Something like that? Yep. Okay. Because we were almost continuous. We were down to a minute. We could have went to seconds, but all right. So this is continuous. Okay. The other loan thing is just a regular loan when they ask you to do that kind of idea. All right. So we have this type of loan thing here. Right here, this guy. Okay. We have simple interest, and then we have continuous. So you just got to hunt through the problem and see, well, what is it asking me to figure out? Okay. Is it asking me to do just a regular loan, simple interest, or continuous? All right. They talk about a doubling time. Like doubling an investment. Okay. And there used to be an old thing called the Rule of 72. They don't even mention that in here because I think it's pretty old. But it used to say that if you take 72 and you divide it by small interest rates like 4% or 6%, then that's about how long it takes to double. So if I took 72 and divide it by 4, it would take about 18 years for the average loan to double. Okay? That's called the Rule of 72. But they don't mention that in here, and they just say, so if you have, like I'm looking at one of the examples in the book here, it says, what annual rate of interest compounding annually is needed, or double loan in 5 years. They have a problem like that. So let's look at that one. So say we're going to use this guy here, 1 plus, we don't know what the rate is, and it is compounded annually, so that'd be 1 there, and we won't know what the time is. We just know we want to double the investment in 5 years. Okay, so we need to know what the rate is. All right, so if we're going to double, then this P, this is going to be 2 times P. Because because we want to know how long it takes to double it. All right. So we should just divide by p here. You can see this is very similar to what we were doing earlier tonight. So we're left with this. Okay. So you say, well, how do we fix that up? Well, we could just fifth root. So we'd have the fifth root of 2 is equal to 1 plus r, and then just use decimals or whatever to find the fifth root of 2. Subtract your 1, and that would tell you your rate. Okay? But the rule of 72 works pretty well to find out how long it takes for something to double. This is like 1.14, right?
Could you leave it as 5, the fifth root of 2?
Oh, no, that's not 1.14. No, you should probably figure it out. I'm going to try to do it on here. I don't. No, that won't work. I have to go 5, root 2, enter. That can't be right.
1.14.
Yeah, 1.14. So then if we subtract, I had it right. So if we subtract 1, that's about 14.14 or 14%, right? Which makes sense because that's going to take a long time for, it's going to be a pretty high rate to double in 5 years. Okay. The rule of 72 breaks down when you're dealing with higher rates, though. Okay. If we took 72 divided by 14, probably not going to get 5. It breaks down a little bit there. Let me see. I can show you a little bit here what I did today. I saw one that was really pretty good. This was the one I looked at. So it talks about here, this little site, I was reading this today, and here's the formula they give to finding your monthly payments. And you can see this is a pretty, here's our formula that we had, interest rate divided by 12 because 12 is being compounded monthly. This is only negative because it's down below it. It would be positive for us, a number of months. And then they put a 1 here. So this is finding your monthly payment. It's not really finding the amount of the loan, but that's where the fancy division comes in. But you can see that this formula is embedded in there, the one that we just went over. So I mean, it's kind of used, but I wouldn't, like it says on here, I was reading a little bit more, and they say that, that car loans, it's a common belief that over 60 months your loan looks like this, linear, which is wrong, and that it has a more of a bow effect here because it's amortized. Okay, so they're paying down their interest first and then the principal, which is how a housing loan is, right? Which is what I knew. All right. So, I mean, if you did this, so if we did, like I was just playing around with it, so 8,000, an interest rate of 10%, oh my goodness, maybe 4, or maybe 5, 60 months, so 150.97, okay, nice little calculator, but they just use this formula to come up with it. Right, and we could do the same thing. If we would just use this, so if we went, here, let me show you. So if we went, get rid of this. Let's see, that's 1, oops, sorry. Parentheses 1, I'll put the number out in front. What is that? What do we say, 8,000 plus interest rate, I think I said was 0.04 divided by 12 to the 12 times 60 months. So it says, wow, it says 87,834. So you see, it's not quite how it works. All right, that's why I said that this formula does not quite work for, I don't want 12 there. I got it wrong there. I need RT, don't I? Oh, no, I have it right, NT. Right, right. It is. But I don't think you'd be paying 87,000. Well, yeah, no.
It's just on it has the top, it shows the actual payment divided by the.
Right. So I was just showing you that that's what this formula does, though. That's why it's not real accurate for.
That shows the final, what you're gonna pay at the.
Right, but if you took this number, 87,834, and divided it by 60, oops, we're getting one. See what I'm saying? Well, 60 times 12. 121.99, right?
Yeah.
But this says it was 150.97. Oh, I have interest rate wrong? I wonder if it was 4 or 5. Here, let's see what happens then. I still don't think it's going to be right, but. One 159,685. 221. Yeah. So see, they're figured out differently. So that's why it doesn't give you a very good, it's just a rough estimate. It's not really that accurate. Okay. But they do use, I mean, this kind of thing is just, it is used in certain other applications of very simpler loan things, and probably more like credit card sort of applications than it is in actual loan situations.
So like the APR, when you get charged interest on your credit card for the month, is that the percentage from the APR? Or? So
the APR, what happens there, what used to happen is that they would say, your interest rate is 8% or something like that, right? So, but when they applied that 8%, they applied it in a month. So over the span of a year, your actual interest rate from the beginning to the end was higher. And that's called the APR, the annual percentage rate. Whereas the rate is just the rate for each time. So that's why they had, I mean, this is a long time ago when they had, the rule came up and they said, well, you guys got to start reporting the APR, you're deceiving people, right? Because there's a difference. I mean, it wasn't very much when we did it, but does that make sense? So now it's all APRs and stuff like that. So all the problems on here are pretty much just asking you to find using those formulas, and it's going to tell you which one to use. You know, where it's going to, if it says simple interest, then you use the one, and otherwise you're pretty much using the other one. So using this one. I mean, it's just a matter of substituting some stuff in. All right, kind of like what we were doing earlier. And that's all there is to that section. It's pretty straightforward. I could do a problem off of there if you want me to, but there really isn't much you want me to do. Are you okay with that formula then, plug numbers in, or? Yeah. Pretty, I mean, you know, it's plug them in. Okay. I wish it was more exciting than that, but sorry, it's not.